All right, what I'm going to be doing here is lab 6. Mark this lab 7, 8, but it's actually going to be lab 6 on the seasons. And normally we'd have this simulation where you do it interactively on the computer. But for these two, this one in particular, I'm going to do it for you because they don't, it works. It's a file that you have to actually upload yourself. It works fine, but I'm going to go through it with you. If you want to get it, the link on there, on the lab handout, on the lab links is there. I'll do that, and then I'll also explain a little bit about the Milankovitch cycles, but that one just has a website for it. As far as Milankovitch cycles, which named the Milankovitch. I'm trying to explain why we have ice ages and in the past, and we'll have them again in the future, a long time from now. So I'm gonna go through the first one. So if you get the handout, all right, I'm gonna go through each one. And so we're gonna look at characteristics at the spring equinox, summer solstice, autumn equinox, and winter solstice. So I'm gonna go through each one of these and then look at the characteristics. So if you pull up the handout, either print it out and look at the video while I go through it, you can complete the answers yourself. So I'll be doing this myself and you can get the answers. So I'm gonna start with this simulation, which I have set up. I brought the default for it. And we're going to set person's latitude. How we can do this is by adjusting person's latitude here, which will be it's about as close as I can get it, about 0 degrees. And all right. What is the latitude of something at the equator? Well, it's 0 degrees latitude. Okay. What we're now going to do is by adjust this. So what you'll see is as we move this around, this will indicate on the calendar what season it is as we orbit around the sun by dragging this. And notice how we'll look at the sun's declination and right ascension on the bottom here. So I'll go through each one. And we're going to start with the spring equinox, where the declination is 0 degrees. Right ascension is 24 hours. Right ascension on March 21st. Notice at the equator, right, the angle of the sun is basically 90 degrees. I can't really get it any closer than that. So the angle of the sun, the altitude of the sun is 90 degrees, okay? So that sets up the first part. While we're at it, we can also, let's go back to here. Notice I can adjust the the orbit. So here we're looking at it side on. Here would be looking at it straight from the sun's angle. So notice how this the amount of daylight is 12 hours. So I'm just going to adjust it so it's kind of like we had before, so we kind of see both. All right, so now we're going to set it to somebody at Bemidji. That's about 47 degrees. And you can see, okay, That's the label. That's our latitude, 47.1 degrees. And the sun's altitude is 90 minus that, so it's approximately 43 degrees. I mean, if we were at 45 degrees, then it would be, the altitude would be 45 degrees. All right, next we're going to go to the North Pole. All right. Due north. Okay, on the equinox, the spring equinox, latitude of the North Pole is 90, and the sun's altitude would be 0. It would be right on the horizons, and the sun's altitude is 0. Now, if we go down to minus 45 south, that's the last question. As close as I can get it. All right, so 45 degrees. Sun's altitude is 45 degrees. So latitude is 45 south for somebody at that location. Here's our declination again and the right ascension. So that's for the first part. Now we're going to go on to the next one, which would be the summer solstice. All right, so now move this up to the solstice. There we go. So on the solstice, June 20th, it's approximately 23.5 degrees is declination, and the right ascension is 6 hours. All right, now if we go back through all this again, so somebody on the equator, about as close as I can get it again. All right, the latitude is same as before. Latitude, maximum altitude is 66.4 degrees on this date. So in the summer solstice at the equator, it's 66 degrees. If we go up to Bemidji, again about 47 degrees. Let's go back to 47. That's our latitude. The altitude of the sun is 66 degrees, almost exactly symmetrical. So it's 66 degrees. So that's the highest the sun gets in June 21st in summer, right? Next we'll go up to the North Pole. And there we have the sun's altitude is 23.4 degrees, which is the same as the declination. And then the last one is somebody at minus 45. Close enough. Sun's altitude is 21.3 degrees, so it's quite low in the horizon. And the sun's So that'd be sun. So at that point, you're in the southern hemisphere. The sun is much lower in the sky at noon during our summer. All right, next thing we're going to do is go on to the equinox, the fall equinox. Okay, get that as close as we can. And we're now doing the equinox, the autumnal equinox. And we again put our person at the equator. All right, as close as we can, good enough. All right, latitude is 0, basically. Sun's altitude is approximately 90 degrees. You can round this to 90, that's as close as I can get. So the sun on this fall equinox, autumnal equinox, is directly overhead. Right ascension is 12 hours, declination is 0. All right, then we go up to Milankovitch. Close enough. Let's see. Let's get that. Good enough. All right. Sun's altitude is 42.2 degrees. And our latitude was before. Going up to the North Pole. Okay. Latitude is 90. Sun's altitude is again 0. It's right at the horizon. So this is at the North Pole on the autumnal equinox. The North Pole will start to experience 6 months of darkness. And then finally at the 45 degrees south. Right, then 45, then the sun's altitude is 45 degrees. So, all right, so that's that, and so that's for the autumnal equinox. We're next going to go to the winter solstice to finish up. Okay. You can see how the tilt is. If we rotate the tilt, North Pole is in complete darkness, while the South Pole is completely lit. So we'll expand this out again. Here's our right ascent. Declination is now minus 23.5 degrees, and the declination is 18 hours. And this is in terms of hours in the sky. If we go to this equator, all right, again, 0. Sun's altitude is 66.7 degrees, 66.5 degrees. If we go up to Milankovitch, now again, we're on the winter solstice. So at our latitude, sun's angle is about 19.5 degrees. So it's very low in the sky. Short time period. The North Pole, all right, sun's altitude is actually minus 23.5 degrees, meaning it's actually way below the horizon. So this is the midpoint of winter. You still have 3 months of darkness to go up there. You can see the sun is not at all above the horizon. And then finally, the last one is minus 45 degrees. Close enough. And at that point, sun's altitude is about 68.6 degrees. So similar to what we have in Bemidji in the summer, this is their summer in the southern hemisphere is in December. So that's the lab part, first part of lab 6. All right, this is the second part of Lab 6, which deals with Milankovitch cycles, as I said. And so here's the handout, which again is available online for Lab 6. And what you're going to do is I'll pull it up and you're going to look at comparing eccentricity, precession, and tilt. And what we're going to be looking at is what exactly changes for all three of these. So I'm just going to click on the link here and show you how this works. So this will be a qualitative type of part. So you look on here, if you go on Lab 6 files, Milankovitch simulations, and what we can do here is then, all right, so we can either get a top view of what happens or an oblique view. And what we're going to look at is if we change each one, eccentricity, what does that mean? All right, notice how the orbit, it's closer here than we can actually, if we slide this up and down, we can notice how the circle changes in size. And this is what happens over a period of thousands of years. The Earth's, what we call how circular the orbit is, changes. And in short time period, it's hard to tell, but in long time period, it changes quite a bit. So this is what we call eccentricity, right? And with that, we get a change in the climate temperature. Or we change that and then click on to precession. And what this is by, if we look at this, notice over a long period of time, normally the Earth's axis is always pointing in one direction. It's always pointed towards the North Star. But over a period of about 26,000 years, the axis actually points somewhere else. Much like a spinning top, the axis will change. And notice how the scale is here, how this changes over tens and hundreds of thousands of years. So if I do it quickly, you know, like abruptly change it 30,000 years, we get that effect. And notice how we get the change in climate due to that factor. And then next one is tilt. And the tilt is, our normally tilt is about 23.5 degrees. But it changes just slightly over a period of 10 to 20,000 years. So it actually changes somewhat. So notice how the axis is actually changing here. So we put all these together, we end up with this kind of change in the global temperature over thousands of years. So it can be colder than normal, warmer than normal, over, this goes back 400,000 years. So we put all these together. We had a time period 20,000 years ago in the Ice Age when it was colder than normal, much colder than normal. We had a period of 125,000 years ago when it was warmer than normal. Here's another Ice Age we have. So we have Ice Ages in the past, but again, these are periods of 20,000 years. This is the reason why we've had climate change in the past, and while we'll have it there, but this does not remotely overcome the effect of CO2 emissions and climate change due to human factors. So this is the lab. As far as that, you can click on the link and open this website yourself. This is sponsored by University of Wisconsin. So that's the last part of Lab 6.